Civil engineering. Introduction.
Civil engineering is a broad field focused on the design, construction, and maintenance of the physical and naturally built environment. This includes infrastructure like roads, bridges, buildings, and water systems, as well as the systems that support them. Civil engineers apply scientific and mathematical principles to create solutions that meet societal needs while considering factors like safety, sustainability, and environmental impact.
Subdisciplines. Civil engineering encompasses various subdisciplines, including
structural engineering, focuses on the design and analysis of structures, ensuring their stability and safety, such as residential and commercial buildings, skyscrapers, industrial facilities, and stadiums. Transportation engineering deals with the planning, design, and operation of transportation systems such as roads, highways, bridges, tunnels, railways, airports, and harbors.
Water resources engineering
involves the management and utilization of water resources by dams, canals, irrigation systems, water treatment plants, and wastewater management systems. Geotechnical engineering studies the behavior of soil and rock to support civil engineering structures such as foundations, soil stabilization, and slope stability.
Environmental engineering focuses on protecting the environment and public health through the design of sustainable systems. Construction engineering and management involves the planning, management, and execution of construction projects. Main courses. Structural analysis. This course focuses on understanding how structures behave under different loads and forces, using principles of mechanics and mathematics. It's a basic course for designing structural elements like beams, columns, and slabs using various materials such as concrete and steel. Concrete and steel structures. These courses delve into the specifics of designing structures using reinforced concrete and steel, including material properties and detailing. Soil mechanics studies the mechanical behavior of soil, particularly in relation to engineering structures. It examines how soil responds to stress, deformation, and failure, and how these responses affect the stability and performance of foundations, slopes, retaining walls, and other geotechnical structures. Foundation engineering. Foundation engineering is a specialized field within geotechnical engineering that focuses on the design and construction of foundations for structures. It ensures that buildings and other structures are safely supported and transfer their loads to the ground effectively. This involves understanding soil mechanics, structural engineering principles, and project-specific requirements. Surveying and geomatics involves the techniques and technologies used to measure and map the Earth's surface, essential for planning and construction. Surveying is the process by which a surveyor measures certain dimensions that occur on or near the surface of the Earth. Surveying equipment such as levels and theodolites are used for accurate measurement of angular deviation, horizontal, vertical, and slope distances. With computerization, electronic distance measurement, EDM, total stations, GPS surveying, and laser scanning have to a large extent supplanted traditional instruments. Data collected by survey measurement is converted into a graphical representation of the Earth's surface in the form of a map. This information is then used by civil engineers, contractors, and realtors to design from, build on, and trade, respectively. Elements of a structure must be sized and positioned in relation to each other and to site boundaries and adjacent structures. Although surveying is a distinct profession with separate qualifications and licensing arrangements, civil engineers are trained in the basics of surveying and mapping, as well as geographic information systems. Surveyors also lay out the routes of railways, tramway tracks, highways, roads, pipelines, and streets, as well as position other infrastructure, such as harbors, before construction. Fluid mechanics and hydraulics covers the principles of fluid behavior, including pressure, flow, and energy transfer, with applications in water resource management and hydraulic structures. Fluid mechanics and hydraulics are closely related fields, with hydraulics building upon the principles of fluid mechanics. Fluid mechanics is the broader study of fluids, liquids, and gases, at rest and in motion, while hydraulics specifically focuses on the behavior of liquids, particularly in engineering applications. Essentially, hydraulics is the applied science of using fluid mechanics to solve practical engineering problems, especially those involving the movement and control of liquids. Environmental engineering
addresses the design and implementation of systems for water and wastewater treatment, air pollution control, and solid waste management.
It focuses on protecting the environment and human health by designing solutions to environmental problems.
It applies scientific and engineering principles to address issues like pollution control, water and wastewater treatment, waste management, and sustainable design.
Environmental engineers work to minimize the impact of human activities on the environment and ensure a healthy and sustainable future. Highway engineering focuses on the planning, design, construction, and maintenance of roadways, including pavement design, traffic management, and safety considerations. It encompasses a broad range of tasks, including road alignment, pavement design, traffic management, and safety considerations. Highway engineers work to ensure efficient and safe transportation of people and goods, considering factors like traffic flow, environmental impact, and future needs. What does a civil engineer do? Structural engineer.
Structural engineering is concerned with the structural design and structural analysis of buildings, bridges, towers, flyovers, overpasses, tunnels, offshore structures like oil and gas fields in the sea, aerostructure, and other structures. This involves identifying the loads which act upon a structure and the forces and stresses which arise within that structure due to those loads, and then designing the structure to successfully support and resist those loads. The loads can be self-weight of the structures, other dead load, live loads, moving, wheel, load, wind load, earthquake load, load from temperature change, etc. The structural engineer must design structures to be safe for their users and to successfully fulfill the function they are designed for, to be serviceable. Due to the nature of some loading conditions, subdisciplines within structural engineering have emerged, including wind engineering and earthquake engineering. Design considerations will include strength, stiffness, and stability of the structure when subjected to loads which may be static, such as furniture or self-weight, or dynamic, such as wind, seismic, crowd or vehicle loads, or transitory, such as temporary construction loads or impact.
Other considerations include cost, constructability, safety, aesthetics, and sustainability. Construction engineer. Construction engineering involves planning and execution, transportation of materials, and site development based on hydraulic, environmental, structural, and geotechnical engineering. As construction firms tend to have higher business risk than other types of civil engineering firms, construction engineers often engage in more business-like transactions, such as drafting and reviewing contracts, evaluating logistical operations, and monitoring supply prices. Coastal engineering. Coastal engineering is concerned with managing coastal areas.
In some jurisdictions, the terms sea defense and coastal protection mean defense against flooding and erosion, respectively.
Coastal defense is the more traditional term, but coastal management has become popular as well. Environmental engineering. Environmental engineering is the contemporary term for sanitary engineering, though sanitary engineering traditionally had not included much of the hazardous waste management and environmental remediation work covered by environmental engineering.
Public health engineering and environmental health engineering are other terms being used. Environmental engineering deals with treatment of chemical, biological, or thermal wastes, purification of water and air, and remediation of contaminated sites after waste disposal or accidental contamination. Among the topics covered by environmental engineering are pollutant transport, water purification, wastewater treatment, air pollution, solid waste treatment, recycling, and hazardous waste management. Environmental engineers administer pollution reduction, green engineering, and industrial ecology.
Environmental engineers also compile information on environmental consequences of proposed actions. Geotechnical engineering. Geotechnical engineering studies rock and soil supporting civil engineering systems. Knowledge from the field of soil science, materials science, mechanics, and hydraulics is applied to safely and economically design foundations, retaining walls, and other structures. Environmental efforts to protect groundwater and safely maintain landfills have spawned a new area of research called geoenvironmental engineering. Identification of soil properties presents challenges to geotechnical engineers.
Boundary conditions are often well defined in other branches of civil engineering, but unlike steel or concrete, the material properties and behavior of soil are difficult to predict due to its variability and limitation on investigation. Furthermore, soil exhibits nonlinear, stress-dependent, strength, stiffness, and dilatancy, volume change associated with application of shear stress, making studying soil mechanics all the more difficult.
Geotechnical engineers frequently work with professional geologists, geological engineering professionals and soil scientists. Transportation engineering. Transportation engineering is concerned with moving people and goods efficiently, safely, and in a manner conducive to a vibrant community. This involves specifying, designing, constructing, and maintaining transportation infrastructure which includes streets, canals, highways, rail systems, airports, ports, and mass transit. It includes areas such as transportation design, transportation planning, traffic engineering, some aspects of urban engineering, queuing theory, pavement engineering, intelligent transportation system, ITS, and infrastructure management. Municipal or urban engineering. Municipal engineering is concerned with municipal infrastructure. This involves specifying, designing, constructing, and maintaining streets, sidewalks, water supply networks, sewers, street lighting, municipal solid waste management and disposal, storage depots for various bulk materials used for maintenance and public works, salt, sand, etc., public parks and cycling infrastructure. In the case of underground utility networks, it may also include the civil portion, conduits and access chambers, of the local distribution networks of electrical and telecommunications services. It can also include the optimization of waste collection and bus service networks. Some of these disciplines overlap with other civil engineering specialties, however municipal engineering focuses on the coordination of these infrastructure networks and services, as they are often built simultaneously, and managed by the same municipal authority. Municipal engineers may also design the site civil works for large buildings, industrial plants or campuses, i.e. access roads, parking lots, potable water supply, treatment or pre-treatment of wastewater, site drainage, etc. Water resources engineering. Water resources engineering is concerned with the collection and management of water as a natural resource. As a discipline, it therefore combines elements of hydrology, environmental science, meteorology, conservation, and resource management. This area of civil engineering relates to the prediction and management of both the quality and the quantity of water in both underground, aquifers, and above ground, lakes, rivers, and streams, resources. Water resource engineers analyze and model very small to very large areas of the earth to predict the amount and content of water as it flows into, through, or out of a facility. However, the actual design of the facility may be left to other engineers. Hydraulic engineering concerns the flow and conveyance of fluids, principally water. This area of civil engineering is intimately related to the design of pipelines, water supply network, drainage facilities, including bridges, dams, channels, culverts, levees, storm sewers, and canals. Hydraulic engineers design these facilities using the concepts of fluid pressure, fluid statics, fluid dynamics, and hydraulics, among others. Civil engineering management. Civil engineering management. Civil engineering looks at a project as a whole, and there are many different roles that a civil engineer must take on, including overseeing the work of other professions who contribute to a project. This specialization will give them more experience overseeing all aspects and organizing a team of professionals so that the job can be completed efficiently. Thanks for watching. For more videos, please like and subscribe.